You being here, it's no big deal. Okay, so now we're going to look at trigonometric substitution. And trigonometric substitution is used when you have integrals that involve factors that look like one of these three radicals. Now, these three radicals look very similar to what you would get if you were solving for one of the legs of a right triangle. As a matter of fact, these three radicals are really the Pythagorean theorem. So, what we're going to do is we're going to draw the triangles to see what the U substitutions are that we need to do for each one of these cases. Now, you can either memorize what the substitutions are, or you can just learn how to make these triangles. I don't memorize the actual substitution, I just recreate the triangle when I'm doing a problem. So, in the first case, well, since there's a subtraction, we know that the Pythagorean theorem is an addition, so this is going to be the hypotenuse, and that's going to be one of the legs. Well, the hypotenuse is A, and one of the legs is U. So by the Pythagorean theorem, this other leg has to be A squared minus U squared. And that's where that factor comes from, a triangle that looks like this. This factor here, well, since it's an addition, both of these are the legs, because if you're solving for the hypotenuse in a Pythagorean theorem problem, you get a sum of two squares. So that means one of the squares is, the square root of one of those squares is a leg, and the other one is also a leg. So we're going to look at that, and that means that this up here is the square root of A squared plus U squared. Right? So that's where that factor would come from, a triangle that looks like this. And this last triangle, well here, once again, U is going to be the hypotenuse because it's having something subtracted from it. Whenever you're using the Pythagorean theorem, the only thing that's going to have anything subtracted from it is the hypotenuse. So that means U is the hypotenuse, which means one of the legs is A, which means that this leg down here is going to be U squared minus A squared by the Pythagorean theorem. All right, now all of these give us different substitutions that we can make. For instance, for this one, if I just focus on these two sides, well, those two sides form the sine of theta. So I know that the sine of theta is equal to opposite over hypotenuse. So that here's the first substitution I can make. I can let U equal A times the sine of theta. So if I have a trig integral that has if I have an integral that has a factor that looks like this is the trig substitution that I'm going to want to make. Here's another one. Well, let's see, I'm going to focus on these two, and those two are the tangent. It turns out that the tangent of theta is equal to U over A, based on this triangle, which means that U is equal to A times the tangent of theta. So if you have an integral that involves a factor that looks like this is the trig substitution that you may want to make. And lastly, here, well, I'm going to focus on these two. Well, those two, I could use the sine, but if I use the sine, I'm not going to be able to solve for U very easily. So I'm going to use the reciprocal function for the sine, which is the cosecant. So in this case, the cosecant of theta is equal to the hypotenuse over the opposite, in which case I see that U, in this case, is equal to A times the cosecant of theta. So, if you have a trig integral involving a factor like this is the substitution. A trig integral involving a factor like this is the substitution. A trig integral involving a factor like this is the substitution. You could memorize that, or you could just learn how to recreate these triangles the way I just did. So let's take a look at an example here. The example that I want to look at is this one here. Example, the integral of x over the square root of 9 minus x squared dx. Alright, so in this case I see that there is this factor down here, and I am going to recreate the triangle personally to see what the U substitution would be. Well, 9 is the positive term and it's a difference, so I know that the square root of 9 is the hypotenuse. So this is going to be a 3, and x is one of the legs, so I'm going to call this x. Here's the angle theta. This down here is going to be the square root of 9 minus x squared by the Pythagorean theorem. So that's how the actual factor fits in with making the triangle. And then that means that I know that, well, I have these two things. That is the cosecant of theta. The cosecant of, actually, not the cosecant. That is the sine of theta. And the sine of theta is equal to the opposite over the hypotenuse, 3. So I get this thing, which says that x is equal to 3 times the sine of theta. This is the substitution that I'm going to make. And I also need to know what dx is. Dx, d theta, the derivative of this with respect to theta, well, the derivative of the sine is the cosine. So that means that dx is equal to 3 times the cosine of theta, d theta. So now I have everything I need to make a substitution. I have a substitution for x, so I can replace the x's. And I have a substitution for dx, so I can replace the dx. So after substitution, this integral becomes this. The integral of x. Well, x is 3 times the sine of theta. 3 times the sine of theta. Divided by the square root of 9 minus x squared, which is going to be 3 times the sine of theta squared. 3 times the sine of theta squared. And then multiplied by dx, but dx is 3 times the cosine of theta. So dx is 3 times the cosine of theta, d theta. So there I have a new integral. Let's see, this integral is the integral of 3 times 3 is 9 sine theta cosine theta over, when I work this out, I get this. Well, 3 squared is 9, so I get 9 minus 9 sine squared of theta. I still have the d theta there. Then I have a factor of 9 that I can pull out. So I get the integral of 9 sine theta cosine theta over the square root of 9 times 1 minus the sine squared of theta, d theta, which is, let's see, the square root of 9 is 3. So I get the integral of 9 times the sine of theta cosine of theta, d theta, over 3 times the square root of 1 minus sine squared of theta. And that 1 minus sine squared of theta is actually the cosine squared of theta by the Pythagorean identity. 9 over 3 is 3, so I can have a 3 in front of the integral. And then I get the sine of theta cosine of theta over, and then that is the square root of the cosine squared of theta by the Pythagorean identity. By the Pythagorean identity, I get this now. The square root of the cosine squared is just the cosine. So this is what I actually have. Let's see, let's back up over here. Yeah, let's back up over here. This is what I actually have now. I have, this is equal to 3 times the integral of the sine of theta cosine of theta over the cosine of theta d theta. These just cancel out, and we get that this is 3 times the integral of the sine of theta d theta. A relatively easy integral to do. So let's see. If I integrate the sine of theta, I get negative 3 cosine of theta. And then all I have to do, oops, I should not have erased the triangle. Let me recreate the triangle here. If you remember, the triangle that we had looks something like this. Theta was here, the right angle was here. We said that 3 was the hypotenuse and x was the opposite side, so that this would be the square root of 9 minus x squared. That was the triangle that we had. So we have to refer back to that triangle to change this back into a function of x. It's now a function of theta. It's a trig function. I need to change it back into a function of x, an algebraic function. So looking at this triangle and what I have here, this is the actual answer, negative 3, and then I just need to know what the cosine of theta is. Well, the cosine of theta, here's the angle theta. The cosine of theta, the cosine is the adjacent side, the square root of 9 minus x squared, over the hypotenuse, over 3. So it's the adjacent side, adjacent over hypotenuse is the cosine. So I get that the final answer to this is negative square root of 9 minus x squared. And there's the final answer for the integral.
Good.